equation, I say this is second equation, and this is third equation. Let us recall why we are doing all this adventure, because we realize that this is longitudinal perturbed equations of motion, and if I want to comment on the dynamic stability of the airplane, I need to track the value of u, w, q, all these perturbed quantities, and depending upon their responses, depending upon how they are changing, we will comment whether the airplane is dynamically stable or not. For example, if I give a small disturbance and u goes on increasing, that is small u goes on increasing, definitely I know that it is not dynamically stable as far as u is concerned, right? Like that w and q, same logic. To solve this equation, we wanted to have the functional form of f x, f z and m, that is to ask a question, how this f x, f z and m depends, or how this f x, f z and m depend on motion variable and control variable, and we have seen this. These are the variations, right? Once I know the value of x u, x alpha, x delta e, all these dimensional derivatives, I can explicitly write f x, f z and m function of motion variables and control variables, and then my equation is complete, or it is in the form where I can solve it. 1, 2, 3 equations I can solve. I can solve using numerical methods. There are so many standard numerical methods are there. I can solve this equation using numerical methods and comment on whether the airplane is dynamically stable in longitudinal mode or not, right? But we will be following a different approach. For that, let me go back to the initial example what we have given as a mass spring damper system. Once we agree that we need to solve this equation in time domain to know how the perturbed quantities u, alpha, q, w, they are varying, and once I know that, I can comment on the dynamic stability using a time domain analysis. But we will see that we will be having a different approach, and to make that understanding clear, I will take you back to the lectures what we started initially for mass spring damper system. Remember, the equation was mx double dot t plus cx dot t plus kx equal to f of t, right? And then what we did, we said this can be written as x double dot plus c by m x dot plus k by m x equal to f of t. Now what we said, if you want to find the natural frequency and damping ratio, then what I have to do? I have to go for Laplace transform. So we wrote it as, we took Laplace transform of this is s x of s plus c by m s x of s plus k by m x of s is equal to 0, because we are looking for characteristic equation. Okay, we put f t is equal to 0, and by doing this, we found equation s square plus c by m s plus k by m equal to 0, and then we compare this with the standard form of second order system s square plus 2 zeta omega ns plus omega n square equal to 0, and comparing this, we found out what is zeta, what is the numerical value of zeta, and numerical value of the natural frequency. So you can decide the value of c and m, k and m to design your system, because this also gives you a condition how do you adjust value of c, k and m so that it belongs to a maybe a critically damped case, maybe an over damped case, maybe an under damped case, right? Okay. Similar approach also will be applying here. That is to say, we will use Laplace transform and find the equation in frequency domain, right? The way we have done it here. What is the advantage here? You could see that this was in time domain, so you need to integrate this equation to find out x of t, a response. But once you are doing in frequency domain using Laplace transform, then this becomes algebraic equation. So your computational effort becomes simpler, right? Okay. And also as a designer, you need to have some expressions or some numbers which are very handy to use. If you every time need to use a computer, you cannot design an airplane, right? Because at the preliminary stage, you should be able to use few well thought expressions and find out the boundaries where the design will become feasible or design will become not feasible, right? From that dimension, you will be using frequency domain, but you can always work in time domain, no restriction on that. So if I now take Laplace transform for these three equations, what do I get? So if I take Laplace transform on these equations, what I will get, first equation what I will get, just see here, I will get S u of s is equal to minus g theta of s into cos theta 1 plus xu into u of s plus x alpha into alpha of s plus x delta e into delta e of s, right? Straightforward. For u dot, it is s u of s, because we know Laplace of x dot is s x of s if the initial conditions are 0. And since we are talking about linear system, the stability will not depend upon the initial conditions, so we can neglect it, right? Similarly, if I see the second equation, I will get s w of s minus u1 q of s is equal to minus g theta of s sin theta 1 plus zu into u of s plus z alpha into alpha of s plus z alpha dot into s alpha of s. Please understand, alpha dot is here, so s alpha of s will come. Similarly, for zq into s q of s. And for the third equation, I can write s q of s is equal to mu into u of s plus m alpha into alpha of s plus m alpha dot into s alpha of s. Again, alpha dot is there. Similarly, mq into q of s plus m delta e into delta e of s. Right? We will do a little bit more trick. We will try to see how can I write q of s using theta of s. Okay. For small perturbation, we will assume that, which is right also, and especially our steady state is a cruise. There is no bank, right? So there is cruise going like this. There is no psi. So I can always write q is equal to theta dot, and hence q of s I can write as s theta of s. If we have forgotten, let me recall, if this is my airplane, if this is my wing chord line, and this is the relative air velocity, and this is the horizontal, then this angle is axis, chord axis to horizontal, this is theta. Which angle? This angle between velocity vector and the chord line, we are talking about alpha, and this angle between the velocity vector and the horizontal is called flight path angle. Gamma, right? So as far as q is concerned, it is the rotation about y axis, and for small perturbation, especially when we are talking about longitudinal motion, this approximation is fair enough, right. So, now what we will do with this? What we will do is, wherever qs is there in this expression, say here it is there, here it is there, we will substitute q of s by s theta of s. Is it clear? This one term here, one term here, I will substitute q of s by s theta of s, and then I will write this whole expression in the matrix form, which will be very simple as long as you understand this. So, now the matrix form equation will look like, let me write, once we will write, the matter will be finished after that, s minus xu minus x alpha, then g cos theta 1, second will be minus zu, then s u1 minus z alpha dot minus z alpha, the third one is minus zq plus u1 into s plus g sin theta 1 and here minus mu minus m alpha dot s plus m alpha, and here s square minus mqs, this into u of s by delta E of s, here alpha of s by delta E of s, here theta of s by delta E of s. This is equal to x delta E, z delta E, m delta E. Matter is closed. Okay, let me check. S minus xu minus x alpha g cos theta 1 minus zu s u1 minus z alpha dot minus z alpha, right, minus zq plus u1 s plus g sin theta 1 minus mu minus m alpha dot s plus m alpha. So, this is something like this. Then this is s square minus mqs u alpha theta, that is fine. You could see here, since we have used this approximation q of s equal to s theta of s, so when we have substituted it here, so now our motion variable are u, alpha and theta, right. So, this is the in matrix form the characteristic equation for longitudinal dynamics, and if you want to find out the roots of this equation, the rule is very simple. The determinant of D will be equal to 0, where D is this matrix. If I write it A x is equal to B, then determinant of, let us say A, let me put it A, determinant of A is 0 will be the characteristic equation, and you will see once you expand it, you can write this whole determinant equal to 0 in a form, the characteristic equation to find the root will become determinant of A equal to 0, and that will imply equation of the form AS4 plus BS3 plus CS square plus DS plus E equal to 0, where A, B, C, D, E will have the expression once you take the determinant of this, and which I will just display it in the next class. But as long as you understand this represents the longitudinal perturbed equation of motions characteristic equation, I need to solve this equation to comment on whether my aircraft is dynamically stable in longitudinal mode or not. What does it mean? You find the root of S and see what is the real part, what is this complex part, or this is a complex root or the real root, what is their sign, and from those you can find out whether the airplane will be dynamically stable or not. So, basically you need to know how to solve this equation to find the value of S. Okay? So, we will stop it here. Next class we will start from this point. Thank you very much.